we go.
So, good morning, everyone. Thank you for joining us for this seminar that will be given by Dr. Ezra Jampole. How do you say your last name?
Jampole's right. You got it.
Thank you. So, Ezra, I've known Ezra for quite some time, since he's based in Stanford when he was running the seismic design competition. And since then, he has moved to New York. He works for Exponent now. He's not just an expert in earthquake engineering, but he's expanded to other issues related to structures, and mainly, or he has done a lot of investigation of failure analysis. And I believe that's what will be the topic of his talk today, and how that gets involved with lawyers, or how lawyers get involved and engineers get involved with that. And Ezra also is still very active with EERI, from what I understand, both locally with the New York chapter and also with the Young Professionals Committee. And I'm sure he will encourage all of you to join, if you're not already members, so that you can learn from what others have done and are still doing on this field. So with that, thank you again, Ezra, for your time. And please.
Thanks, Andres, and thank you to all of you at the University at Buffalo for hosting me as part of EERI's Friedman Family Visiting Professionals Program. I first want to thank the Friedman family for sponsoring this program. It's typically in person, and it's unfortunate that we can't do it in person this year, but probably for the better. And I hope to make a visit to Buffalo in person at some point. And one benefit of this is that the lecture is recorded. So if you really enjoy it, you can watch it as many times as you want. So I'm going to talk about legal and insurance disputes in earthquake engineering specifically. I do a lot of failure analysis that goes beyond earthquake engineering, but since this is sponsored by the Earthquake Engineering Research Institute, it seemed wise to focus on some of the earthquake disputes that I've been involved with. But first, I'll give an introduction to EERI. It's a great organization, and hopefully my couple slides on some of the activities of EERI provide encouragement for folks to join EERI, to get involved in the very active student chapter at Buffalo, and then to get involved in the local and potentially the national network within EERI upon graduation or before too. EERI was established in 1948. It is a leading nonprofit organization dedicated to earthquake risk reduction. It is very multidisciplinary. There are engineers, geoscientists, social scientists, urban planners, all interested in reducing earthquake risk overall, but coming at it from a different perspective. And something that EERI brings is really this multidisciplinary perspective to earthquake engineering that's quite powerful for advocating for earthquake risk reduction from a policy perspective, as well as, of course, the technical aspects as well. EERI's, I would say that their most key program that they're most famous for is the Learning from Earthquakes program. This is the flagship program. Historically have conducted reconnaissance after many earthquakes. Recently, they have reconnaissance reports from Japan, Oklahoma, New Zealand. They produce many webinars discussing these events. And they also produce clearinghouses after earthquakes, where folks upload their photos, their videos, reports, links to news articles, and it really is a good resource for both industry and for researchers if they want to learn about an earthquake and don't necessarily want to wait the many years for the detailed studies and reports to come out. There's a lot of information that goes into clearinghouses relatively soon after the earthquake. So I'll tell you a little bit about how I got involved with EERI, and maybe that'll spark some of you to get involved with EERI. I think most people attending the call are students, and so have an opportunity to take a similar path that I did. When I started in graduate school at Stanford, I was a mentor for the Seismic Design Competition team, and from there joined EERI's National Student Leadership Council, and ultimately rose to co-president of that council. And they planned the Seismic Design Competition nationally, come up with the rules, and so if any of the students are here, back then they could have bugged me about what the new rules were going to be and get a head start, and I of course would have stonewalled them. I also, towards the end of my time in graduate school, started getting involved with the earthquake clearinghouses, especially following the 2015 earthquake in Nepal. I curated a topic on housing for the clearinghouse. also been published in Earthquake Spectra. And over the last few years, I've been involved in some field reconnaissance in coordination with EERI, particularly after the earthquakes in Oklahoma in 2016 and the Mexico earthquakes in 2017. And I'll talk a little bit about that experience next, because it's probably what most folks are most interested in at this phase when they want to get involved with an organization like EERI. I was the co-chair of the Younger Members Committee until about a month ago, and I would say thankfully my term is over, because it was a lot of work, but it was very rewarding. It's a great way to connect with other younger members within EERI until you're no longer fooling anyone that you're young. At a certain point is what perhaps happened to me. And finally, something that I would encourage students and young professionals to get involved with is EERI's travel study program, especially if you haven't done field reconnaissance before and you're interested in getting into that. EERI has this great program where they'll bring graduate students, young professionals, younger academics to an area that was recently hit by an earthquake, and you spend a week there touring the damage, talking to people who went through the earthquake, talking to emergency responders, and seeing how the community is recovering long term. I was part of that program that went to New Zealand a couple of years ago now. And the photo on the right is me standing next to a fault, and this was obviously subject to a landslide and some permanent displacement vertically of that fault as well. So I promised that I would talk a bit about some of the exciting things that happen in earthquake reconnaissance. So I'll take a brief detour into the Mexico earthquakes before I move on and talk a little more about EERI, and then get into some of the legal issues. So the Mexico earthquake, this is the Puebla Morelos earthquake, occurred September 19th, 2017. It was normal faulting. The earthquake occurred here, which was quite far away from Mexico City, but you can see that, and this is more traffic light coding of how intense the earthquake is, there was intense shaking in Mexico City, despite it starting to attenuate out in other areas, and we'll talk in a minute about why that happened. There was an earthquake early warning system in place. It was put in place after the 1985 earthquake. It was far away. It was 300 kilometers away. And you can see that the location of this earthquake with normal faulting was in between where the earthquake early warning system stations were and Mexico City, which was hit hard by the earthquake. So people started feeling the earthquake about 20 seconds before they got the early warning in some cases. Additionally, this earthquake was on the anniversary of the 1985 earthquake, so there were drills, I think at 11 a.m. local time, and some people probably thought that when the sirens started going off a couple hours later, that was a continuation of the drill in remembrance of the 1985 earthquake. So that would obviously affect your decision-making on whether or not to evacuate a building. So some background information on Mexico City. This is what it looked like in the 16th century. This was the Aztec city of Tenochtitlan. And you can see that it was basically an island with a lake around it. And the Spanish eventually took over and they filled in this lake. And so what Mexico City looks like today from approximately the same angle, you can see this mostly filled in. The consequence of that is that there are very soft deposits in much of Mexico City, basically a lake bed that has been filled in. And so when the earthquake shaking comes, it tends to excite very particular frequencies in certain locations in Mexico City. And so certain structures tend to be targeted. So I'll show a couple example structures that were damaged in the earthquake. This is one. It was an automotive facility. You can see some cars being repaired here. And one thing to note off the bat is this is a soft story structure, relatively rigid, solid walls in the upper levels with some windows. And then at the first floor, there's these relatively small columns. So we see what happened to the structure after the earthquake. We have a pretty dramatic collapse as well. And on site, taking some photos after the debris is cleared, we can see that there was unreinforced masonry. Some of the columns didn't have any stirrups in them. That's a problem as well. And so this is the type of structure that would be very susceptible to a dramatic failure like what occurred. I'll show another example of a structure in Mexico City. This is a taller one around the height that tended to be targeted by the earthquake on the soft soils. And in this case, this one was at the end of a row of structures, and it extended a little bit higher by a few floors than the structure that was actually at the end. And so it was confined at these lower levels, but at the upper levels, we see a failure. And this was likely at least partially attributed to the fact that it was confined at these levels below, and then above we see a fuse at this level that has collapsed onto the level below. And I believe it's the 5th story. So what did our reconnaissance team do? It was a collaboration between Exponent, RMS, and a company called One Concern that is trying to figure out where first responders should go after earthquakes. And we were an EERI reconnaissance team and produced an EERI report after the earthquake. And we looked at over 700 buildings, and we primarily focused on areas around ground motion recording stations. So here's an example of one of the recording stations that we looked at. This looks like about 50 structures right around the recording station. So we had a fairly good idea of what the intensity of the shaking was at all these structures because they were quite close to the recording station. And the reason we did this is there were many seemingly similar buildings that had very different performance during the earthquake. And so we were interested in what really fundamentally is driving the damage and what types of structures potentially should be targeted for retrofits or further study after the earthquake. And so we looked at about 13 recording stations, I believe, for these 700 structures. And then based on the data we collected, we're able to develop some fragilities based on different structure properties. And this was relatively coarse. I would say we looked at ranges of numbers of stories that would fall into the bands of periods that we expected for that type of structure that would be targeted by the earthquake. And so we divided it into, say, buildings 1 to 3 stories, 4 to 9 stories, and then 10 to 20, for example. We looked at how old the structures were, whether the building was at the end of a row of buildings or in the middle. Buildings at the end tend to serve as fuses. And we looked at where the structures were, if they were on firm soil or within that lake bed zone, whether they were retrofit or not retrofit. And then if they had key features to them, like if they had a soft story, if they had a short column, if they had some sort of irregularity, like vertical irregularities or horizontal irregularities as well. And then we could develop these types of curves to estimate what level of damage we would expect for that type of structure, and had some interesting findings that I'm not going to present here, but wanted to give you an idea of the types of post-earthquake reconnaissance that can go on in conjunction with the EERI, who typically serves as a hub for reconnaissance teams. So if that hasn't convinced you to become an EERI member, there are a couple other reasons that I'll talk about here. There's the interdisciplinary aspects. It's very effective for doing research. If you know what people outside of just structural engineering are doing. There are opportunities within EERI, no matter what level you're in, from being a graduate student to a younger professional to being a very experienced professional. And there's regional and national activities as well. As a student, there are a lot of benefits to being a member. You might not consider it a benefit right now if you're not enjoying my talk very much, but there's this Friedman Family Visiting Professionals program where lecturers travel typically around the country, in this case virtually. There's the EERI competitions, like the Seismic Design Competition, student paper competitions, and fellowship opportunities. And there's travel grants to attend the EERI conferences, plus access to Earthquake Spectra, which is one of the premier journals in earthquake engineering. And so I'll just say that after graduation, there's some clear paths for what to do next. As a graduate student, you can join the Student Leadership Council. You can get active in the Younger Members Committee. You can join the regional chapters. Even just as a working professional, most student chapters have professionals who will help the seismic design competition team. There's also postgraduate internship opportunities with EERI that are a great way to meet people who work in the field of earthquake engineering and learn what very diverse folks across many disciplines are doing in the earthquake field. I think the EERI interns have been really successful when they go into practice after their internship. Because they know so many people and they really have a full perspective on what happens in earthquake engineering. And then you can also join that travel study trip and travel to places like New Zealand. I don't know where the next trip is going to be, but I'm sure it will also be an interesting one. Another benefit to EERI, well, After graduation, you get your first year of young professional membership for free and reduced rates for 4 years. So that should be some incentive to join as well. So lastly, if I haven't sold EERI to you properly or haven't turned you off of it completely, I encourage you to visit EERI.org, which has far more information on EERI and has information on all the great committees you can get involved with within EERI. So that was a good place for me to take a sip of water as we transition to the meat of my talk, which is related to legal and insurance disputes in earthquake engineering. And at this point, I will let it be known that I am okay with questions as I go along. I will have a number of questions for the audience that I hope students will or others will chime in for. I'm happy for you to venture a guess. This will hopefully be a little interactive, and it's not the same as in person, but I think we'll do our best. So when I talk about legal issues and insurance issues in earthquake engineering, I'm really talking about when something has gone wrong on a project and the lawyers get involved. Parties are disputing over what happened, why it happened, who is going to pay the cost, whether it's a criminal penalty or a civil penalty or things like loss of licensure. And I think you can break these down into 3 primary areas that I've worked in. One is performance issues. So this, for example, is a structure in Mexico City that had a number of fatalities. And so there are cases where there are performance issues where you either have collapse or have other issues related to the performance of the structure during an earthquake or some other hazard. There are design issues. And so one example here is if a structure is designed in a way that someone says is incorrect and it either needs to be torn down or redesigned or retrofit, or it can't be used at all, or you need to change its use occupancy, then there are legal issues, and often experts will get involved and give opinions on whether or not the design is correct or not. And then there's also construction issues, so whether or not something is built the right way. And so one example of this is if there's a defect in a structure or not. And I'll show an example on the left. This was a structure where partition walls were installed, and there was an allegation that they were installed incorrectly and they could not take what the IBC required load was laterally on the walls. And so we tested them in situ to determine whether or not they actually could take that load. And then on the right is an example of delays. Often there are design issues that might drive delay in a project. And many construction contracts have provisions where if a structure is delivered early or it's delivered late, there's financial consequences for the parties that are involved. And so often what drives delays, it can be construction issues, it can also be engineering design issues. For example, if you design something incorrectly and you have to go back and fix it, and that causes you to be a month or so behind schedule, then that would be a design-driven delay. And so we will occasionally investigate those in conjunction with folks who are assessing what's truly delaying a project, whether the design was on the critical path or not. So when we perform investigations into failures, there are key questions that we ask. What has caused the failure? That's obviously quite important for assigning blame. Has the structure performed or been designed appropriately? The way that we design buildings for earthquakes, for example, we expect that there's a certain amount of damage during a certain intensity of earthquake. So you might have damage, but maybe the building was designed to experience that type of damage during that intensity of earthquake. Can the structure be repaired? This is a pretty critical issue. Often there are allegations that, well, the structure can't be used at all anymore, or that the structure is fine and you should be able to get back into it right away, or at least you should be able to repair it. And so we will often investigate whether or not the structure can and should be repaired from a safety perspective, and let others worry about the cost side of things. And ultimately, who's responsible when something has happened, whether it's a design issue, a performance issue, or a construction issue. And so Exponent will typically get involved. We are hired by attorneys for the owners, for designers, for contractors, for insurance companies. other stakeholders. We work for all types of parties, and we will investigate and provide our independent expert opinion on what happened and why it happened, as we're instructed. So our failure investigations typically include some combination of the following. Not all include all of this, and maybe I'll highlight a couple things where you might not do one or two of these. We very often perform visual inspections of what has happened. We'll perform destructive or non-destructive testing in some cases if we feel we need more information on, say, what the strength of the concrete is. We'll hypothesize different potential causes of failures. We'll perform numerical modeling sometimes. Often it's not necessary. You might look at something and know what happened right away. We'll review contemporaneous information. We'll write reports if requested. If there are other experts who have different views, we might rebut their evidence or continue our independent evaluation by considering things that they've said. And if the parties are not sick of the dispute at this point and they can't settle their case, then we will give depositions, or we may testify in court or in arbitrations regarding whatever the incident is. So I'm going to give a couple examples of types of investigations that I've been involved with. All of them will relate to earthquakes because this is an EERI talk. There are many interesting other failures that don't relate to earthquakes, and I hope that Andres invites me back in the future to give a talk related to some of those, because they are quite fascinating. I'm not going to say that it's unfortunate that we don't have more earthquakes in the US, because that would certainly lead to more interesting talks, and so I'm glad we don't have that many big earthquakes. But some of the more dramatic failures that I've seen are not earthquake related. So I'll talk about a post-earthquake investigation. So that's a case where there has been damage because of an earthquake. And then I'll talk about a case where there are allegations that the earthquake resisting system, its capacity was reduced because of some other type of event that happened at the structure. And then I'll talk about a case where there are allegations related to whether or not the design was sufficient to resist the anticipated earthquake loads at the structure. So I'll start with the post-earthquake insurance investigation. So we'll start with one where we see some alleged earthquake damage. So to provide some context to this, I think it's important to touch on what has happened in the insurance industry after past earthquakes. And in particular, I'll talk about the 1994 Northridge earthquake. There was roughly, and this is subject to dispute. I don't think anyone knows the final figures, but one that I've heard commonly cited is between about $25 and $40 billion in insured losses following the earthquake. About half of that was to light frame structures, like the one that I'm showing here. And the losses were so extensive that the insurance companies became nearly insolvent. And now we have more of a state system for earthquake insurance in California, for example. Now, the importance of this is that insurance companies becoming insolvent is a bad thing for everyone, no matter how you feel about the way that insurance companies may have treated you personally in the past. If the insurance company goes out of business, you may have a legitimate claim that they were going to pay out, that they may not have the funds to pay out. So that's not a good thing. So it's very important to get impartial, independent investigations of the damage that has occurred after a natural disaster to figure out what has actually been caused by that natural disaster, so that appropriate payouts are made by quantum folks who calculate that, not something the engineers do. So I'll show a case study from Oklahoma. And this is from the 2016 Cushing, Oklahoma earthquake. This was a magnitude 5 earthquake that sounds small, but it certainly has potential to cause damage. Here we're seeing the MMI for the earthquake and a red dot that I've unfortunately put over the title of the town, which was very close to the epicenter, within a few kilometers. So the expected damage that we would see from this type of intensity earthquake, that's something that I highly recommend looking at it before you ever go out to investigate a structure or to perform field reconnaissance. It's good to know what you should be expecting. This earthquake was close to the epicenter, was mostly in the moderate or strong category. So a lot of people will feel the earthquake. Contents will be thrown around in many cases. and you might see some cosmetic damage to structures. And I will note that this is on the border of very strong, and these damage states are not set in stone. This is just what we've seen for this intensity of shaking in past earthquakes. So it's not completely unexpected that you could see for certain structures that are more vulnerable damage that goes beyond this. So I'll show one example structure from that earthquake. This was a building in the historic downtown that when the EERI team got on site, and I was a part of this team, you could see that the building was leaning, I think, at least 1 degree. You see it on the right side. I've drawn some lines to show that degree of lean of the building. We can't all stand there in person to see it, so the cameras only do it so much justice, but we can see that the brick is separated from the adjacent structure, and we can see that on the far side a bunch of bricks have fallen out of this. And so this is an interesting case. I think at the time I recall on site there was one of the stakeholders in the building had gotten an engineer to evaluate the structure, and he had told her that it was fine. You could push it back into place. This would be fine. And that's probably not something that I would recommend for an unreinforced masonry structure that was leaning by 1 degree after an earthquake. I think this would be at risk to potentially more damage and maybe even collapse during an aftershock. And sure enough, this building reportedly came down, or at least the front facade did, during a wind event a few months later. And so the current status of it is that the building has been removed entirely. So we can see from this earthquake that there is potential to cause damage to at least certain types of structures from this magnitude 5 earthquake. In this case, to an unreinforced masonry structure that was pretty heavily damaged. So where we were involved was in looking at alleged damage to school buildings in the Cushing earthquake. And I show a map here where we see the epicenter and we see some of the school buildings, and then we see the MMI contours around that. So you can see that all these buildings are relatively close to the epicenter of the earthquake and are in those approximate damage bounds that we saw looking at MMI. So there's 9 school buildings. Here is an overview of those structures. For the most part, that they were masonry structures, often reinforced, and this varied somewhat from building to building. There were some variations. I think there was steel framing in a couple of these buildings as well, but the predominant construction, we would see masonry walls with brick facade. And here's a close-up of one of these structures. So you can see the scale of it. There's 1 story for much of the building, lots of classrooms here. And then there was another side facility that was either an auditorium or a gymnasium. I think this one was a gymnasium. And one other thing to notice, and you can tell by looking at the roofs, are that these are different vintages of construction as well. These buildings were built gradually over time. And this applies to, I think, nearly all of the structures. It wasn't built in one shot. They're built over time. So I will show a couple photos of the type of damage that we saw on these structures, and I might ask the students to chime in on whether or not they think this damage was caused by the earthquake or not. So if anyone wants to be brave and decide whether they think that the ceiling grid condition would have been caused by this earthquake, now's your chance to chime in.
Is that from pipes rupturing by any chance? Because it kind of looks like water damage.
So we have what's scheduled on the
Yeah, so the tricky thing about this structure is this particular building was unoccupied at the time of the earthquake and hadn't been used for a number of years. So I might struggle to attribute that to pipes bursting. So ceiling grids are very frequently damaged during earthquakes. They respond under very low accelerations. And so this is the type of damage that you might expect to see even in relatively low intensity shaking. The fortunate thing is that, well, in this case, some of them are broken, but if your grids don't break, you can put them back up. An exception is if the grid system itself is damaged. And this is something that we see where the grid system will move back and forth, and in this case, hitting against the masonry wall, and so that can be damaged and may need to be replaced. So this is something that we would attribute to the earthquake. So here's another example, perhaps folks will chime in on. This is a masonry wall that we can see at the base of the wall that it appears to have shifted relative to where it originally was located on the carpet. So does anyone want to venture a guess of whether or not this might have been caused by the earthquake?
I'll go with yes.
Yeah, this is it was, I guess, a 50%er. So this is a non-load bearing wall. So we don't see this condition throughout the rest of the building. This appears to be potentially some local shifting of this wall, maybe caused by the earthquake. But there aren't a whole lot of other indications of damage to the wall, something I'll point out. So maybe there are anchorage issues with this wall, which is why it was able to move. So I'll show another example, and this is interestingly at the interface between different vintages of construction. And so this is at the slab on grade. This is right at the interface there, and we see cracks underneath the carpet at that interface in some topping slab. Caused by the earthquake or not caused by the earthquake? And again, these are all yes or no questions, but I'm happy if folks want to expand on their answers.
I want to go with yes, but can you also explain like what is it they've used for the interface?
Right, so the interface, I don't know what is between these, if there's been any dowels between the slab from one structure to the structure of another vintage.
Usually they don't connect the two buildings, right? Like if they
often not. It depends, but often not. So this one is maybe not caused by the earthquake. If you have structures of different vintage, you may have different settlement rates as well for that soil. And so that's something that could very easily also cause this type of cracking. Earthquake could exacerbate it. That maybe is possible. But the impetus for this, probably not the earthquake.
Okay.
Another example, this is an interesting one. This is in a gymnasium of one of the buildings. We see these steel trusses that are supporting the roof system, including this overhang. And we see a separation between the overhang and this masonry wall. We can see it a little more clearly up here. And if we go to the outside, and this is not the exact same location, but it's a similar condition, we see a lot of stepped cracks in the masonry wall. And so I'll give the answer on this one. This is something likely not caused by the earthquake. There's no real connection between these two. We can look at the load path of the structure. If we can see the load path, there really isn't a connection between this truss and the wall. So in places like Oklahoma, where you have a lot of soils that can expand quite a bit throughout the year, it's very common to see settlement like this, where you'll see walls pull away from structures that aren't really attached to them, which is the case here. We also see in the corners of a lot of structures, and I've highlighted in black to make it easier to see, we see a lot of cracks, and this is something that happens often during earthquakes if you have walls that don't have interlocking blocks between them. And so this is something that maybe is caused by the earthquake, but is not a serious condition. We also see cracks that emanate from the corners of openings. And one thing that we often look for is if you see cracks in all four corners, well, the earthquake will move the structure this way and then that way. And so you might expect to see cracks in all four corners. But when you see them in only one corner, then especially at the corner of a building as well, then it's maybe more likely that this was caused by things like settlements. And maybe I'll pose this question to the audience of whether or not this damage to the fascia board, which has come out, has come off. We see it, someone has stashed it in the railing here, whether or not this was likely caused by an earthquake.
I'll go with no. More likely
No,
wind.
and yeah, wind, that's exactly right, Chris. There's not a lot of mass here. It's hard to imagine that an earthquake would cause this type of damage, but it's something we very frequently see in wind events. And lastly, here's a case where we see some slight cracks and we see some soil eroding away from foundation. And this is something that also likely not caused by an earthquake. And something we often will look at is the aging of the damage. In this case, this is very weathered. So it's unlikely that this was caused by the earthquake. This is a condition that happens over a very long period of time. And then the last thing we might look at are cracks that occur in between blocks. And in this case, there were allegations that cracks like this and potentially some stair step cracks as well were also leading these buildings to be unsafe and have significantly reduced lateral capacity in the structures. And so the type of thing that we would do is we would look at the cracks, and then we would look at the published literature on the type of damage that we would expect and how much that would reduce the capacity of the structure when you see this type of cracks. So in this case, we have one that is a classic example of minor damage to a structure that doesn't really reduce what the capacity is of the structure, and you don't actually need to repair it to restore the structural performance. So in summary, I think you've probably have gotten the sense that my view at least is that there's relatively minor damage to these structures. You do see things like cracks, but nothing that would compromise the structural integrity of the structures. So it's important to be able to look at that in the context of the insurance industry to make sure that proper damage is being attributed. We don't want insurance companies to go bankrupt. So in summary, things to consider is if the extent of damage, if that's likely to target particular elements, whether you expect to see that damage or not, whether or not there's weathering, and then to think if earthquake makes sense as the cause to the damage. And that wind example that Chris helpfully answered is a good one. Doesn't really make sense that earthquake would cause that damage. So this, I would say, is a common type of project that we do when there's insurance disputes related to relatively small earthquakes. So now I'll move on to another example, and this is of a 12-story building that is a very different story to those low-rise buildings in Oklahoma that we were looking at. So this building is 12 stories. It was built in the 1920s with a reinforced concrete frame with hollow clay tile infill and partition walls. And this was damaged during the 1994 earthquake, and it was subsequently repaired. So this is a long time ago, it was damaged. Now, there were allegations that a water supply line leaked at the 8th story of the structure. It damaged the plaster over the walls. And in the course of removing some of that plaster, the hollow clay tile infill was damaged. And so I show here the location of the alleged water damaged plaster. And so the allegation is that the hollow clay tile infill was a critical portion of the lateral resisting system for the building, and that the earthquake resisting capacity of the structure was substantially reduced by this damage to this hollow clay tile infill that maybe leaked down all the way to the 1st story from the 8th story. So we were tasked with providing an independent view on these allegations, whether or not it's correct, whether or not the earthquake resisting capacity of the structure was reduced or not. So I'll give you some background on the way these allegations were supported, and then maybe give folks a chance to try to rebut it and then show you what we came up with. So someone created a numerical model of this structure using fairly common commercial software, and they modeled the reinforced concrete frame, and then they modeled the infill of the hollow clay tile using equivalent struts that span from corner to corner in some frame. Pretty common way of modeling these. You convert the infill wall into these struts. Now, what they did was they said, well, let's look at the capacity of this undamaged structure, and then let's make an assumption of what the damaged structure is. So they took a wall layout that applied solid hollow clay tile wall infill between every single concrete column. And they said, this is our undamaged case. And then our damaged case is going to be, well, if we remove all of those walls in the line of action where there was the water leak and the alleged damage to the hollow clay tile infill, and we run our analysis in this case, you can intuitively see that this induces an irregularity in the structure, and potentially you would get a torsional response in this structure. And so they analyzed this case, and they compared this undamaged case to this damaged case. And then what intensity earthquake did they analyze it to? Well, they took the very famous 1940 El Centro earthquake recording. They took one component of that ground motion, and they scaled it down to 10% of the actual earthquake record. And that has 0.03 Gs. And they ran their analysis with 0.03 Gs. And based on that analysis, they determined that there were differences in the way that the damaged structure versus the undamaged structure performed with these two layouts of hollow clay tile infill. And based on that, they said that the lateral resisting system for the building was reduced, and then it's up to construction folks for the costs of what happens after that. So we investigated this issue. And so maybe I'll pause for a second, and if anyone has ideas for whether they think this analysis is correct, or if they have any specific issues with the way that this analysis was done by another engineer. I think the faculty are free to chime in too.
So I would ask on this, did they look to do the same analysis at the actual level of shaking that was observed to see, because yes, if there is some introduction of damage by missing those brays, great. But if you have the full level of shaking and the same level of damage occurs with or without those struts, it seems like it would be kind of a moot point.
That's a good point. No, so the Northridge earthquake was 94, and I should have said this, I might not have, but the alleged incident was in the 2000s or the 2010s. So the other engineer did not run an analysis with the observed shaking from a couple decades prior. They only ran it with this intensity.
About the analysis, did they, the plan views that you showed, it doesn't look like the walls were connected all the way to the frame. So doesn't necessarily, it's not necessarily an infill in the first place. So that might be wrong in the analysis.
Excellent point, yes.
Yeah, question. Like, I've never had any experience with hollow clay tiles, but does that have any structural capacity? Like, I've never heard of that used as a structural component.
That's a very fair question. So hollow clay tile is often used in flooring systems, and back in the day used in flooring systems, and also used for infill. There is some capacity if you fill it up and completely infill that wall. Yes, there is some capacity, and there's even published literature on what the capacity is of that hollow clay tile if you're completely filling the wall between the walls or columns and between the floor slabs.
But wouldn't it matter what the intent of that was, if that hollow clay tile was just meant to be a partition, or if it was meant to have structural capacity in the original design? I mean, don't you have to know what the original engineer's design intent was?
Well, and you do and you don't. Whatever the intent was, the design is, and it was built as it was. And so you can estimate what contribution that hollow clay tile makes to the system, whether it was built one way or not. Though I will say your point on the partition walls is a very good one. Often we don't bring partition walls all the way up to the bottom of the slab of the level above. And so that would be a case where you're probably not providing very much confinement to that hollow clay tile. If it was actually being used as infill, then you likely would see that going all the way up to the bottom of the slab or the beam. So, okay, I got some very good responses. So I'll show you the answers, I guess is maybe the best way to put it. So first, does hollow clay tile actually resist earthquake loads? So if you have a solid hollow clay tile infill, the answer is yes, it does. You can form these struts, these compression struts, and you can resist earthquake loads. The challenge is that when you start having openings, you don't resist nearly as much load than if you have no openings. So for example, if we have a window with 12.5% of the area, there's a 30% reduction in the stiffness of the structure. That's quite a bit. If you have a couple doors, and this is taken directly from this structure, the doors represent 42% of the area of this wall, and there's an 84% reduction in the stiffness. So if you have openings, which structures do, certainly on the exterior and also on the interior, you really don't have that much contribution from the HCT. And as Cinna pointed out, when we look at the actual floor plans, it really doesn't look like these are solid walls, because they're not. There are a lot of openings for windows on the exterior. There are many doors in the interior as well. So the consequence of this is that by assuming that there is solid HCT infill in the structure, every single column line, you're overestimating the contribution of the HCT infill to the initial stiffness, and you're probably overestimating the potential torsional irregularity of the structure as well. So our investigation also looked at something that I think it was either Chris or Gregory pointed out, which was, well, what shaking has this building actually been subjected to relative to what this other engineer is subjecting it to reach his opinions? And if we compare a record from the Northridge earthquake that was about 1 kilometer away to 10% of El Centro, well, the Northridge earthquake is more than 10 times as intense. So we've already seen how the structure performed, and there was damage to the structure before that was repaired. But that sort of gives us an idea of whether or not the structure can survive or not. So I'll pause here and ask another question of what are the actual consequences of analyzing a building with a lower intensity than you realistically would expect to see the building subjected to?
You might not fully realize your actual load path. Because for a really low level of shaking, you might have a lot of, either unintended or over-relied upon components resisting the earthquake compared to, the full earthquake effect.
Yeah, that's very good. Anything else?
Well, you're just going to underestimate the expected damage overall, right? I mean, the bigger the earthquake, the more damage you should expect.
Yeah, it is funny to draw opinions on whether or not the structure has major issues based on subjecting it to a very tiny earthquake that doesn't really give you an idea of of what the true intensity that you'd expect to see at the site. So I'm going to come back to this load path point because it relates to what we came up with. And this has to do with what the stiffness of the HCT is. So we typically expect that as the earthquake intensity increases, the displacement in the structure will increase as well. Now, if we look at what the backbones are for the various components, looking at the force versus the displacement, well, our concrete frame has this type of backbone curve. And the hollow clay tile infill, the way that it was modeled was with these elastic struts. And depending upon the expected deformations, it would have different stiffnesses. And sure enough, as you expect when there's infill, once you start cracking and spalling some of the bricks, that's not providing a whole lot of resistance. So at low deformations, before you'd see that, the stiffness of the HCT is relatively high. At medium deformations, it goes down, and at high deformations, it's not providing much contribution to the structure. And so the consequence of this is that if you analyze this structure under a very low intensity, you're maybe in this range with low deformations. And so that will overemphasize what the stiffness contribution of the HCT is to the structure relative to the concrete frame, compared to if you were to analyze at a higher intensity where you expect higher HCC deformation, you have lower HCT stiffness, it doesn't contribute as much compared to the concrete frame. So we analyzed this structure under that Northridge record, and we saw deformations that were far greater, quite expected from our perspective, compared to the 10% of El Centro. And we also looked at those 10% of El Centro records and analysis results. And when you zoom out and look at it in the grand scheme of the type of deformations you'd expect in this structure, there actually really wasn't much of a difference between the damaged and the undamaged response case. And that's because it really is the concrete frame that is the primary lateral resisting system, maybe with a little bit coming from the HCT, especially at low deformations, but it doesn't change the response very much. So a summary of our findings, and this is something that I didn't show because it's more of a material science thing. There wasn't actually evidence of damage to the HCT. So the fundamental premise of this was flawed. But even if there had been damage to the HCT, there would have been limited effect on the lateral capacity of the building. And the building had already undergone much larger earthquake than this contrived 10% of El Centro and hadn't collapsed or anything. So it would be unreasonable to say that there were fundamental issues with the lateral resisting system because of the slight damage to the HCT. So I have one more example of a different case. So instead of a structure that has been damaged or a structure that has allegedly been damaged and had reduced earthquake capacity, we're going to look at the dispute related to the design of a structure. And this one's a bit shorter than the other examples. I think I'm running out of time. So I timed this example well then. So this is an underground metro system in a high seismic area. And a new metro line was being built in this high seismic area. And the contractor filed for compensation for delays that they say were caused by the owner because the owner raised concerns over the earthquake resistant design of the metro stations. So the owner was saying that, well, hold up one second. We think that there are some issues with your design. We want you to look into that. That fairly obviously delays the process. And the way these contracts work out, there's incentives for finishing early and there's disincentives for finishing late. So there was quite a lot of money at stake. This was a massive project. And so it matters whether or not the owner rightly raised concerns over the earthquake resisting design of the metro stations. So I'll show you a little bit on the way that they were designed, and then I may poll the audience again on if there are any issues with that design procedure. So here's a summary of the initial seismic analysis. An importance factor of 1.3 was used. So this is an important structure. There was linear elastic analysis of a single station under a 1,000-year return period earthquake. And the conclusion based on that analysis was that the structure would behave essentially elastically under this earthquake. And so the design was suitable. And this is what the owner raised concerns over. So was it reasonable for the owner to raise concerns over the earthquake resistant design of these metro stations? Now I'll pause and give folks a second to think about it and chime in if they have any issues with the way that this design was performed. Appreciating that I've only given you a very high level overview of the key ways that they did the design.
How did they select the hazard that they used?
Right, so there's a couple components of the hazard. There's selecting what intensity of earthquake to use. The importance factor plays into that. And then there's selecting, say, earthquake ground motions, for example, to subject this structure to. So they followed what they thought the relevant codes were.
I just have one question about the conclusion. I mean, they had a linear elastic model and then they concluded the behavior was elastic. I mean, what other expectations would you have from elastic model? I mean, I think that that was something.
Yeah, it's hard to reach a conclusion other than that. You can look at strain limits, for example. So even in a linear elastic model, I mean, we do this. Well, I don't do it, but designers do this quite often where they'll analyze a structure for linear elastic and they use various factors to amplify the response and then compare that to what the limits are. And if they exceed those limits, well, then they either can beef up their structure or they might need to run a nonlinear analysis. But yeah, your point is well taken and a very good point. Okay, so I think we've hit on some of the key things already. So the first thing is related to importance factor, and you might need to be very familiar with codes around the world. But for this type of structure, a metro station in a high seismic area, it's unusual to use that lower importance factor. The structure is more on par with essential structures, which call for greater importance factors. And to put this in terms of how this changes return periods of earthquake, It's the equivalent of going from like 1,000-year return period earthquake to a 2,500-year return period earthquake if you use an importance factor of 1.5 versus 1.3 at this particular site. So on that basis alone, the structure probably wasn't designed for the right intensity of earthquake. So another key thing that Sina has helpfully pointed out again is related to using linear analysis. So especially in conjunction with the earthquake intensity perhaps not being selected correctly, when you have a linear analysis, you're only ever going to get linear results. With a nonlinear analysis, you can only slightly increase the intensity and see your structure really take off in terms of the deformations. And so on this basis, if your intensity is wrong and you've only done a linear analysis, it's hard to extrapolate to the actual performance of your structure only with linear analysis. So there'd be very good reason to then perform a nonlinear analysis. Another issue that folks didn't pick up on, but that's fine, is they only conducted the analysis for a single station. And in this metro system, there were multiple stations, and I'm showing a different area just to not reveal the location of the project. But you get very different intensities, very different expected intensities at different locations. So when you have multiple stations, typically wise to perform a separate analysis for each one, not to only analyze a single station. So after these concerns were raised, there was subsequent seismic analysis that was performed, and this was nonlinear analysis of the single station using a 2,500 return period earthquake that was more in line with what probably should have been used initially. And they analyzed the structure with a single earthquake ground motion. So any issues with this?
Why they only use a single ground motion for it?
Exactly, yeah. A single ground motion is not a representation, an accurate representation at least, of the hazard at a site. And they were using, if I recall correctly, PGA as the intensity measure, which makes some sense for an underground structure. And so an example that we showed was, well, you can have the same PGA subject two different ground motions with that PGA to the same structure and see very different responses, one that might be concerning for the overall performance and one that is maybe less so. So using a single ground motion was not a good idea. So our findings were that based on the issues related to the hazard intensity selected, analyzing only a single station, then analyzing it with nonlinear analysis using only a single ground motion, it was appropriate for the owner to raise concerns regarding the seismic design and analysis of this metro system. So that's it for my examples, but I do have some parting words. I think there's a lot of grad students on the call here who have probably seen the academic side of things quite a bit, and maybe occasionally get some insight into the world of forensics and failure analysis. If you want to avoid a failure analysis, which I would advise most people, it's wise to read the codes and standards, stay up to date on the latest research. Going to grad school is a great way to do that. I think your mind is sort of fixed in that way from all your projects and all your research to do those things anyway. An important thing is not to design out of your depth. A career is a marathon, not a sprint. So you don't need to be an expert on everything right away. You should expand your knowledge slowly. And then if you're a designer, whenever you make key decisions, think about how you would testify about them. Because one day, if something goes wrong, you might end up testifying about those. And then if you really want to avoid a failure analysis, I mean, you can drop out of structural engineering, though at this point, hopefully people won't do that. So if you want to get involved in failure analysis, well, there's, I think, a couple ways to do that. You could ignore the previous slide, and then you'll be involved, but probably from the perspective that you don't want to be involved in, as someone who's subject to the dispute and not just giving an independent opinion on what happened. I would recommend staying in school for a master's or a PhD. It's very useful. We get very unique projects in earthquake engineering and related to other disasters and other issues with designs. And it's very helpful to have that type of background that you can really look in depth at the analysis that was done and then perform your own analysis. So with that, thank you. I hope I didn't go over my time, and I'm happy to answer any questions.
Thank you, Ezra. Very good, very nice. I will open the floor for questions. Just before we hang up at some point, it might be good to, if you stop sharing your screen and people put up the camera, it would take a screenshot of videos.
Oh, yeah, sure.
It will be pretty nice for the report to EERI, the annual report, even for the department Mathematical newsletter.
Do you want to do that now so we don't forget?
Sure, yeah, let's do that. So if you guys can put up your cameras, so if you have one. Thank you. There's some more people.
This is a lot easier than organizing a photo in person.
Exactly.
Good, we just had our almost last.
Okay, I think you have quite a few.
I mean, this, so like.
Someone else should also take one, just in case mine goes bad or something. So we'll have some redundancy there. Okay, very good. Thank you all, and hello to everyone. So we can go back to questions to Ezra.
Nothing juicy yet. We're not sharing.
So I have a question, just because you're talking about this presentation in general from an insurance perspective. You talked about the Mexico City damage for some of these adjacent buildings, and I was wondering if you've ever done inspections on buildings that were adjacent to these taller and deficient structures.
Yeah, that's kind of like what.
Yeah, so we, especially in New York City, do a lot of adjacent construction projects where, and it's not necessarily earthquakes, but whenever someone builds something or has a structure that is close to another structure, there's a chance that you could damage those adjacent structures, whether it's shaking back and forth during the earthquake or when you're driving your piles, for example, or setting up your supportive excavation. That's something we very often do.
Thanks.
And I don't think I've done one where a structure was allegedly damaged by an adjacent structure that hit it. That I haven't done, though have maybe seen some examples of pounding damage in Mexico City and in Oklahoma as well, probably a couple other places, but that just hasn't been subject to dispute.
Yeah.
Other questions for Ezra?
Sure.
I have a question about the last case that you had to, I mean, you were involved in that compensation filing. So how did you get involved in the first place? Like, and what did you have to do at the end? Like when you sided with the owner, was it a report or was it like a testimony? How does it usually look like?
Yeah, and I would use the caveat that we're not siding with anyone. We're just providing our independent opinion.
Yeah. I mean, when you decided that the owner was right, I mean.
Yeah, that it was reasonable for them to raise concerns. So typically what we'll do is we'll write a report with our findings. Sometimes we don't. And this is the interesting thing about failure analysis is we give a lot of bad news to people, but bad news from their perspective, there's always the silver lining that do you really want to go into costly litigation if you're going to lose because all the experts are going to say that you were in the wrong here? Probably not. And so that's really good information that helps them decide what they want to do, if they want to settle the case, if they want to fight it at all, or just pay out. So it's very important that we just give our independent opinions. And much of the time, we will then write reports on what our findings are. And then if they don't successfully settle the case, then we might give depositions or give testimony. And I think in that case, we give testimony.
I see. Thank you.